Thank you for inviting me to this conference. So, today I will basically talk about some result on quantum information theory that we got with Benoit Collins a few years ago. And then I will talk about the main key ingredient of the proof, which was some method of interpolation between random matrices and free operators, as well as some more recent results on that topic. So to start with, I will start with the quantum information theory part. So we'll start with the application, and then I will move forward to the ingredients of the proof, basically. Where am I? There? Oh, okay. All right. So to begin with, let me give some very basic definition in quantum information theory. So what is a quantum channel to begin with? So basically, if we assume that we have two Hilbert space, well, we say that the quantum channel is a linear map between the operator space on those Hilbert space, and we assume that this map is completely positive, trace preserving. So this is the formal definition, but basically what you should keep in mind is the example below. So this thing here, which basically is going to take a matrix of size Kn, take the partial trace, that is, takes the trace on all of the block of size n, and gives you and the resulting matrix will be of size K. So that's more or less like that's the most basic example you can think of, but it turns out that like what we're working with in for those results is not so far from that actually. All right, so then let me define a few more notions. First, the notion of entropy. If we have a non-negative self-adjoint matrix, then we define its entropy as basically the trace of x times the logarithm of x. So the classical notion of entropy is the integral of x logarithm of x. Well, here we replace the integral by the trace, basically. And then if we have a quantum channel, then we can define the output entropy, well, the minimum output entropy, which is I think it was a notion introduced by Ion Nishita, Benoit Collins, and probably a few other names that I'm forgetting. But basically, if we have a quantum channel, we can study its output on the set of matrices D, indices D, which is basically the one that I define here. Is it? Yep. So the set of matrices which are positive and whose non-renormalized trace is equal to 1. And we define the minimum output entropy as h min of phi, which is just the minimum of the entropy on the image of D by the quantum channel phi. All right? So let me motivate a bit all of those definitions and explains why those quantities are interesting. So to do so, let me introduce some more definition. Basically, if you have a quantum channel phi, you can define its classical capacity as the following, which is basically just the limit of a renormalized version of the whole-level capacity of phi. So you take phi, your quantum channel, you tensorize it n times, you take the whole-level capacity, and then you divide by n. And the idea is that this classical capacity is basically, it tells you how much classical information you can have going through your quantum channel. So this is really something that, for people from quantum information theory, is a quantity which has a lot of interest. And as you can see, we have that limit, but it's obvious that if chi was additive, in the sense that chi of phi tensorized with chi of psi was just chi of phi plus chi of psi, then this thing would be constant equal to chi of phi, and you would have that the classical capacity of phi would just be equal to its whole-level capacity. So that would be much easier to compute. And it turns out that this whole-level capacity, which I will not define or talk more about in this talk, is said to be additive if and only if the minimum output entropy is additive. So basically, if you want to show that the classical capacity is equal to the whole level capacity, you basically need to show that the minimum output entropy is additive. And once again, what do I mean exactly by additivity? Well, I mean the following, which is that if you have phi1 and phi2, then the minimum entropy of their tensor is equal to the sum of their minimum output entropy. All right? And now, before I talk more about the results that we got with Benoit, let me just mention that it was proved that actually this quantity was not additive, which is unfortunate because this means that there are no easy way of computing the classical entropy with respect to the whole level capacity. However, for a time it was believed that actually it might be possible because there were some examples where you actually had that C and Chi were equal, so it was far from trivial, basically. All right, but let me now define a counterexample, which is the one which was introduced by Belinsky, Collins, and Nikita. So we have some parameters, k and n, which are natural integer, and we take a sequence of natural integer dn, such that dn is basically it's basically just kn times some constant real number between 0 and 1. Then we consider U, which is a random matrix distributed according to the Hardt-Measure on U kn of C. So it's basically the Lebesgue measure on the unitary group of size kn. Then we have Pn, which is the canonical projection from well, it should be Ckn to Cd, I think, but well, anyway. It's basically the matrix which is zeros everywhere except on diagonal where we have D entry 1. And finally, we define our quantum channel like that. We take the matrix X of size D. We take its conjugate by our isometry, which, yeah, so it does go from CD to CKN. And then we take, once again, its conjugate by U, the random matrix. And then finally, we take the partial trace, which I was talking about on the very first slide. So as you can see, this thing, well, it's not as trivial as the first example I gave in the talk, but still, it's not so far from it. We are just conjugating by PU. And so to define a counterexample, well, we have defined a first quantum channel, phi n, but we also need to define a second one, so that we can show that the phi n and the second quantum channel, that their minimum output entropy is not additive. And to do so, well, we just take the complex conjugate of phi n. So what is the complex conjugate? Well, it's the very same quantum channel, except of taking the random matrix U, we take the conjugate. Not the adjoint, the conjugate. All right, and a direct consequence of this definition is that the minimum output entropy of phi n and phi n bar are the same, basically. It just comes from the fact that you can take the conjugate of Pn x Pn star, and that will be the same thing if x is a positive random matrix, positive matrix. All right, and so consequently, what we're going to do is to prove that the probability that we do not have additivity is positive. And so if we prove that the probability that such an inequality happens, that if we prove that this probability is positive, then as a natural consequence, there will be a deterministic example that satisfies this thing. Because of course, if you can show that deterministically this thing never happens, then the probability should be 0. All right. So first, we want to start by basically bounding this first entropy, because it turns out that even though that quantity is random, because it depends on a random matrix, well, actually, there is a way to bound it deterministically very sharply. And this is due to a theorem of Hayden and Winter, which basically picked a very specific state, so a very specific matrix X, and apply the quantum channel phi n tensor phi n bar in this state, and show that these, the resulting matrix have some spectral properties, which lets you deduce that actually the entropy of this matrix is sufficiently well, close from some constant that I denote by CKT. And we basically just replace the minimum output entropy of phi n and phi n bar by this constant. So basically, if I go back to that slide, we had that we wanted to show that this probability was positive. Well, now what we need to do is to show that this probability is positive, because we just replaced h min of phi n and h min of phi n bar by 2 h min of phi n, and we replaced the minimum output entropy of the tensor by CKT. Then, just to remind you of the definition, basically the minimum output entropy of phi n, once again, is just the minimum over the output of phi n of the entropy. So that's just the minimum of h of x for x in the output of phi n. And what is this output? Well, we just denote it by k n kt. It's a random set and depends on the parameters n kt and, of course, well, the randomness itself. And so what are we left to do? Well, we want to show that this probability here is positive. So, OK, how do we proceed? Well, we proceed by studying the set k and kt. It turns out that you can show fully deterministically that actually this set has an alternative definition, which is much easier to work with. Because, of course, well, if you just write that as phi n of d, well, you're not going to go very far. But it turns out that because we picked a quantum channel, because we defined it as we did, well, k and kt is actually equal to this thing, which is basically just an, a lot of intersection of a half plane, basically. And it turns out that what is nice is that in this definition, well, the only random part is in this norm here. And it is known in free probability that actually this quantity, this random quantity, is almost surely going to converge towards what I call the, well, what was called the T norm of A. And so it's only natural to assume that this random set will converge towards this deterministic set, where we just replace this thing by its deterministic limits. It's non-trivial to do, but so far it's not the hardest part of the proof. And this is basically what Belinsky, Collins, and Nikita did. And as a consequence, because the convergence happens for the host of distance, well, you get the entropy on the set k and kt is going to converge toward the entropy on the set kt. Or rather, the minimum of the entropy of the first set is converging toward the minimum of the entropy of the second one. And you can actually compute this minimum on kt of the entropy on the set kt. It's something highly non-trivial, and it's something that I think the authors of the original paper were a bit afraid of. But it turns out that there is some sort of a computation trick, which I'm sure Ian and Benoit can tell you more about if you want to know, that tells you that like this minimum on h is actually, you can actually compute it explicitly. And we denote it by a constant skt. And most interestingly, it turns out that this constant skt is strictly larger than the constant ckt over 2. So what do we get, basically? Well, we get that this thing here is going to converge towards a deterministic constant, which is strictly larger than this. So what does it mean? Well, it means that the limit of this thing, of this probability, is just 1, basically. And so by showing that the limit of this probability is equal to 1, it means that for n large enough, you can find, you can show that this probability is positive. And if this probability is positive, it means that you can find deterministic matrices such that your quantum channel defined with those deterministic matrices is not additive. So, all right. So back when Benoit and I started working on that project, the aim was basically the following. Can we get some sort of explicit constant, well, some estimate with explicit constant, sorry, on when does this probability, when does this additivity violation happens? Because so far in the previous theorem, all we have shown is that for n large enough, you have additivity violation. But it doesn't really tell you when this thing happens, like for which size of your matrices you need to consider, basically. Well, to do so, we basically decided to like take that probability and follow their original proof, but then use some new element which lets you prove the same result from the same like original counterexample, but by using different method, you can get some explicit computations. So to do so, the very first step is basically to relate this probability to another one, which is the probability that your random set, which is the random output of your quantum channel, is included into the deterministic limit up to some epsilon kt, basically. Where epsilon kt is like fully explicit, it's fully deterministic, it's just something small. And so just to remember, this thing, this k nkt, is a random set. And it's defined as like a multitude of like an infinite intersection of half plane. And as I was saying a few slides ago, since this quantity is random, well, the set at the limit is defined by replacing this thing by its deterministic limits. Well, this thing converges towards a constant norm t of A. So the limit is just that thing replaced by the deterministic equivalent. So you would believe that it shouldn't be that hard to quantify the difference between k nkt and k kt, simply because, well, we're just replacing that quantity by a deterministic equivalent. But it turns out that it's not so easy, because here we have an intersection of an infinity of half plane, and it can sometimes be quite tricky. Like typically, what you should keep in mind is the following. So you have two lines like this, and you have another one like this. Well, if you move those two things by, let's say, epsilon, the distance between the two lines, well, it will move also of epsilon. But now let's say you have this line. Well, if you move those two lines by epsilon, then suddenly the distance, which is in between those lines, can move by quite a bit. And so that was something that we were a bit afraid of, because here we have an infinite intersection of half planes. So we literally have that scenario happening an infinite number of times. Well, it turns out that it's not actually a problem, and that we actually only lose a factor 1 over k, which was much better than anything we were expecting. Like, if we had to do something with like taking, for example, an epsilon net and working with that, it could have been quite messy. But no, we have that fully determined. Like, we get this thing, and it's basically deterministic, the proof. There are no randomness involved. All right. So now let me explain actually how to quantify this probability. Let me forget actually about there exists A in dk, and let's just study the probability that this norm is larger than the limit plus epsilon. So to do so, like one very classic trick to do, which was, I think, first introduced by maybe Hagop and Torbenson, when they could be older than that, because this part is not the hard part of their paper, but basically you want to study the convergence of this norm towards the limit. So to do so, what you do is that you consider a non-negative smooth function, which is equal to 1 as long as you're larger than this, as like x is larger than this. So f of x equal 1 for x larger than this, and f of x equals 0 if you're smaller than this t norm of A. And so basically, if you have that this probability, well, if you have that if you have that this event happens, then that means that the operator norm of these things is larger than this constant. So that means that you have an eigenvalue of this matrix, because it is self-adjoint, which is larger than this thing. And so that means that the function f evaluated in that eigenvalue is equal to 1. So in particular, if you sum over all of the eigenvalue of f of this matrix, you get that this sum has to be larger than 1. But what is this sum exactly? Well, it's just the trace of f of this random matrix. And so basically, you get that this probability is smaller than the probability that the trace of f of this random matrix is larger than 1. And then you just do Markov inequality, and you get that this probability is smaller than the expectation of this thing. And if you want to show now that this thing is small, you basically have to show that this thing is small. In other words, if you consider a smooth enough function, you want to show that this expectation is small. But as you can see, this is far from trivial, because the trace here is not renormalized. So let's say that this thing was the identity, that this f was the identity, then this quantity would be of order kn, and you want that to go towards 0 with respect to kn. So clearly, you need to be quite careful with that. Typically, there is no way to just approximate your smooth function by a polynomial, for example. That wouldn't work in that case. And so more generally, you will want to show the convergence of, well, that this thing is small for any smooth function under the right assumptions. But then this will mean that the limit of this norm is converging towards this thing, which is something which is far from trivial. I think this was first proved in 2012 by Camille Mal and Benoît Collins. And this kind of things, which is basically the notion of strong convergence for random matrices, is always a tough problem. There are no easy way around. But OK, it turns out that thanks to like some previous work of mine, you can actually like get estimates on those things, and that lets you conclude basically, because in the previous theorem, in the previous slide, you had that we wanted to estimate these things, and what I just told you means that you can do so as long as you ignore this there exists a belonging to dk. Well, then what you do is that you take an epsilon net over dk, you sum over it, you look at all of the probabilities, you do some concentration estimates, and in the end, you get some results, basically. So typically, we computed some, here are like some explicit parameters for k, t, and n, where you do have that additive evaluation happens with extremely high probability. But in practice, what we get is the concentration estimates on the probability that you have additivity violations. I refer to the paper if you want to take a look at the full constant and all of that. But all right, now what I want to talk about a bit more is how exactly can you study these things? How exactly can you like get those estimates? Because this was really the core of the proof, basically. I mean, at least the main technical result, let's say. So to do so, let me go back to some basic definitions. And then I will draw a parallel between the classical world and the free world, basically, and explains how the intuition from the classical world can let you deduce results in free probability. So you have that in classical probability, if you have a Markov process with a generator, L, then you have a list of well-known properties, which are, well, you probably need some assumption on your Markov process to make sure that all I say is true, but I do not really care about this in these slides. I just want to give you some intuition. The idea is that, well, the fact is that the differential of the expectation of f of xt is just the expectation of the generator applied to f, then evaluated in xt. You also have that if your Markov process has an invariant clause z, then xt will converge in low towards z. So what does it mean? It means that if you want to interpolate between the expectation of f of z and the expectation of f of x0, so x at time 0, well, this is just the limit of the expectation of f of xt minus the expectation of f of x0. So here I use the convergence in low of xt towards z. And then, well, you can just look at these things, take the integral between 0 and t of the differential, and then let t go to infinity. And since the differential of this expectation is this one, then you just get that this difference is basically equal to the integral between 0 and infinity of the expectation of L of f of xt. And you actually also get that if x0 is, has the same law as the invariant law, then actually, well, everything is constant, and the differential is the differential of a constant function, so it's just 0. And so the term under the integral is 0. All right? So all of that is like well known in classical probability. But what is interesting is that in the free world, most of this actually can be translated with like, well, free languages, basically. So what do I mean here? I mean that instead of taking a classical Markov process, you take a free Markov process, xt, and then you also have some infinitesimal generator, and then you also have that actually, instead of having that the differential of the expectation of the f of xt is equal to the expectation of the generator evaluated in f, then evaluated in xt, you have that the differential of the trace of any polynomial evaluated in xt is converging towards the trace of your generator evaluated in p, then evaluated in xt. So basically, what I did was just replacing your smooth function f by like a polynomial, and replacing the expectation by the trace. You also have that your Markov process can have an invariant distribution z, and then once again, your Markov process xt is going to converge in distributions towards z. But this time, the convergence in distribution is not the classical notion, but the free notion. So this is the convergence of the trace of any polynomial evaluated in xt. So once again, following what happened on the previous slide, what this means is that the trace of p of z minus the trace of p evaluated at, in x at time 0 is equal to the integral from 0 to infinity of the trace of your generator evaluated in p, then evaluated in xt. And you also get that if x0 has the same distribution as the invariant distribution, then once again, the trace of p of xt is constant, and the term under the integral will just be 0. All right, so you're probably wondering where I'm going at the moment. But let's go back to this notion of interpolation. So now we assume that we have a free Markov process which has an invariant distribution, and whose invariant distribution is u. We also have like some, let's say, some random matrices un, and we consider the two Markov process, free Markov process, utn and ut, which are like respectively studied in un, your random matrix, and u, where u is your invariant law. So then, well, you consider a polynomial q, and you get that this quantity, which is the limit of the trace of q evaluated in utn for t going to infinity, and this thing, which is just the trace of q evaluated in ut, well, in u0n, so un basically, well, this thing is just equal to this integral, where this term here can be computed. And now, if you assume that your random matrix un is converging in distributions towards u, where u is the invariant law, then what this means heuristically is that in some sense, un is close from u. But then if you are close from u, what this means precisely is that this thing is basically converging towards this, because this is the process starting in un, and this is the process starting in u. But as we said, this thing here is actually 0, simply because this is the differential of the trace of q of ut, where ut is starting in the invariant distribution. So this is the differential of a constant term. And so what this means eventually is that we have some sort of like estimate between what happens at infinity and what happens at times n. And this, we write it under the form of an integral between 0 to infinity of this thing, and that heuristically this quantity has to be small. So if this quantity has to be small, that means that this integral should be small too, and that we can quantify the difference between those two terms. And so that's precisely what I did back in 2020. And then I refined that theorem later on in 2023 so that we could actually iterate the process and get this expansion, basically. So, all right, let me talk a bit more about the theorem, give you a few more definition, and explain to you a bit more why it's important for our result. So you basically consider the following. You consider UN to be independent either hard unitary matrices or GW random matrices. For that talk, you only need the hard unitary case, but I just mentioned it. You take P a self-adjoint polynomial, and you take F a smooth function. As I was saying previously in the slides, you need to be able to consider a smooth function. And then you can basically find fully deterministic constant alpha I P of F, so a constant which depends on the parameter P and F, such that this expectation here is the sum of those constants normalized by n exponent to I, plus some error term, which is basically as small as you want, as long as your function f is differentiable. And maybe most importantly, you have that if the support of f is disjoint from the spectrum of p of u, then actually those constant alpha I p of f, they're all 0. So what this means is that if you have a function f whose support is disjoint from the limiting measure, well, you get that those constants are always 0, and that this expectation is basically as small as you want. If you take f to be c infinity, you can take k to be as large as you want. You can actually even take k to depend on n and get some like some exponential minus n concentration estimate, or maybe exponential minus square root of n. Oh, well, it's in the paper. One thing I did not mention here is that you can also consider like deterministic matrices. So you have un, and then you also have zn. Then those function alpha I p of f also depend on zn, but you can also show that they are equal to 0 under the right condition. And then you're basically in the case that I was talking about a few slides ago, where I was saying that you need to be able to master those, to control those parameters, well, those quantities in order to get results. All right. So there has been a few refinements, but I will talk about those later on. Now what I want to say is just a quick overview of the proof of these things, or rather the intuition. So we want to prove that equation. So what do? We consider a polynomial Q. You could take a general function, but for the sake of these slides, I will just take a polynomial. In practice, what you do is you take a Stieltjes transform or a Fourier transform, and that's how you get to work with general smooth function. And you consider this polynomial Q to be evaluated not only with like unitary matrices, but also in free unitary Brownian motion. And so why free unitary Brownian motion? Well, because free unitary Brownian motion are free Markov process whose invariant law are free hard unitaries. And what is a free hard unitaries? It's the limit of the distribution of hard unitary random matrices. So we take this polynomial, and we just interpolate between un, which is the random matrices, and u, which is invariant law, with the help of your free unitary Brownian motion that I was talking about 2 slides ago. And then basically what happens, which is almost magical, is that actually those computations, which seems a priori quite daunting, well, you can do everything explicitly. And you can actually deduce that there exists some sort of some operator t such that this term under the integral is exactly the expectation of the trace of t of q, renormalized by this quantity 1 over n squared. And so from the moment where we have this, we have basically won, because as you can see, we just iterate that process, and every time we do it, we gain a term of order 1 over n squared. And so yeah, that's basically the idea. You can view this t of q as a polynomial in parameters un, ut, vt, which is basically just a polynomial in un and more free unitary Brownian motion, and you just iterate the process. Oops. And so by iterating that process, you get precisely that expectation, that formula. Sorry. All right, so now I'm more or less done talking about the proof of those things, and I would like to talk about some more recent development, within the last year, basically. and things which basically relates to other talk in this conference. So typically, what Benoit will be talking about in this week is about Weingarten calculus. And what is Weingarten calculus? Well, basically, the fundamental question of Weingarten calculus is, how do you compute that quantities? So what is that quantities? It's just, well, you look at the entry of a R unitary random matrix, and you want to compute the integral with respect to those entries with that law. So what this means is that if you take a look at those uij and you use the fact that you can rewrite that as a polynomial, well, as a monomial in u star, and the matrices eij, which are just deterministic matrices with coefficient ij equal to 1 and every other coefficient equal to 0, you basically get that those quantities are an expectation of the trace of a polynomial in deterministic matrices u and u star. Except that this is precisely what I've been talking about for the last few slides, that this is exactly the kind of quantities that we have been working with. And so you can study these things with the method that I was talking about in the previous few slides. And you will actually get that if you just for the sake of notation, the renormalized trace will be denoted by tau n, well, you get that this expectation of tau n of p evaluated in un and zn, well, this is the deterministic term plus 1 over n squared times the expectation of the trace of some operator delta evaluated in p, once again evaluated in un and zn. And so, well, what do? You just take these things, send it on the other side, and you have this operator identity minus 1 over n squared delta, which is equal to something which is fully deterministic. There are no more randomness on the right-hand side. And then what you want to do is basically to replace p by the inverse of that operator times p. Because then by doing so, here you have the expectation of the trace of p, which is what the original quantity you want to compute. And on the right-hand side, you have this thing which is fully deterministic. You have no more randomness there. And you can actually do so. Like, there is a way to formalize that. This is not, of course, this is not trivial, because this operator, well, this operator is defined in a way that is, it's not exactly an operator on the set of polynomial. This is an operator on the set of trace polynomial. But the point is that if you consider the set of trace polynomial of dimension at most d, then basically delta acts on that space. It does not increase the degree. So what this means is that delta is a linear operator which acts on a finite vector space. And so what this means is that this delta as an operator has a bounded norm, and so for n large enough, this thing is smaller than, like, the norm of this thing is smaller than 1, and hence you can actually do all of that like in a formal way and get some like asymptotic some power series expansion of the quantity on the left. All right. So basically, yeah, just as a conclusion, what these things let you do is like find some sort of alternative to Weingarten calculus, but there are lots more things to study, because the combinatorics behind Weingarten calculus has been studied for like 10, 20 years, and it's quite powerful. And I wish I could just use it to deduce some things on those operators delta, for example, go the other way around. But this is a future research. All right. Another recent development, which is also the paper was published last fall. It's a joint paper with Kevin Schnelly. And this time we wanted to study this, like random matrices with this law. So what is that law, basically? Well, forget about the potential V for a moment. Then the law of these things is just exponential minus sum over I of the trace of xi squared, where this dxi is the Lebesgue measure on the set of Hermitian matrices. So basically, if you forget about the V, this is the joint law of d GUE random matrices. And if you add some joint potential V, then you get what we call a matrix model, which is actually the name of the model of the matrix. And so this is something that you can study. And so basically, by doing more or less what I was talking about in the last few slides, you can also find operator delta and nabla v such that you also have that this random matrix satisfies exactly this set of equations. So on the left-hand side, you have your random matrix model, with which you integrate with respect to mu, well, this measure. And on the right-hand side, you get something fully deterministic, which is the trace of a polynomial evaluated in free semicircular. And then once again, what you want to do is basically just replace p by the inverse of that operator times p, so that you get that these things can be computed as such. Well, it turns out that this time there is really no way of inverting that operator, at least when nabla v, when v is different from 0. Because when nabla v is when v equals 0, then nabla v equals 0, and then in that case you get that delta is actually well, the degree, how should I say? Well, delta is nilpotent. And so since delta is nilpotent, you get that identity minus a nilpotent operator is always invertible, and so you can always do so. But when when v is different from 0, then you just cannot do so. However, it turns out that there's a way where, like, if you replace v by lambda v, and you look at like some sort of expansion with respect to lambda and n, then there is a way of making that rigorous, which is basically like satisfying enough for all of our purpose. And so that also means that if you consider that that integral, which is the free energy of your model, well, you can also compute it simply by using that the fact that the differential of the log is actually the expectation of the trace of v, basically. So that does give you a lot of information. So yeah.
So just to know what you're talking about, your random matrix model is you take decoupled matrix x1 xd of size n.
Yes. Like this mu n is the joint law of x1 n all the way to xi. Yes. And so all of those polynomials are polynomials in d variable, and those d variables are all matrices, well, random matrices. What was I saying? So yeah, those things basically let you compute all of those quantities, and out of that you can deduce some result on, for example, graph enumeration. You can deduce some result on the free entropy of the limiting law. So you can deduce some things, but I'll send you back to the paper if you were interested by this. All right, so thank you very much for your attention, and if you have any questions.